Video restoration is the task of recovering high-quality videos from low-quality inputs degraded by noise, blur, compression, or a combination of these factors. Unlike image restoration, which relies only on spatial information, video restoration leverages temporal redundancy across frames, repeating structures, consistent motion, and coherent dynamics to achieve superior results with greater efficiency. But here's the challenge. Real-world videos rarely suffer from just one type of degradation. Instead, they're often corrupted by multiple time-varying degradations, noise in one frame, blur in the next, compression artifacts later on. This dynamic nature makes restoration extremely difficult. Most existing video restoration methods are designed for specific degradation types. Even recent all-in-one approaches, which aim to handle multiple degradations within a single model, typically assume that each video is affected by only one type of degradation at a time. That's not realistic. Enter LaverNet, recently proposed as a step toward more practical all-in-one restoration by modeling time-varying degradations. But even LaverNet and similar models face two fundamental problems. First, degradations like noise or blur can dominate the temporal modeling process. The model starts focusing on the artifacts themselves, patterns that look similar across frames, rather than the underlying video content. As a result, it fails to capture meaningful temporal correlations. You can see this in visualizations. Frames with the same degradation look more alike than frames showing the same scene, confusing the model. Second, these models rely on massive architectures, often tens of millions of parameters, to handle complexity. They scale up instead of solving the root problem. This hides the difficulty rather than addressing it. We ask, can we build a truly effective all-in-one video restoration system with a lightweight architecture? Our answer is LaverNet, a compact, 362K parameter network that achieves state-of-the-art performance across diverse degradations and datasets, using less than 1% of the parameters of existing models. How? By introducing a novel mechanism called selective propagation, inspired by the selectivity principle in Mamba, a recent architecture for sequence modeling. Here is how it works. In traditional video restoration, features are propagated from one frame to the next without discrimination. But if the current frame is noisy or blurry, those corrupted features get passed forward, contaminating the temporal stream. LaverNet changes that. It uses a Selective Propagation Module, SPM, that dynamically estimates which features are degradation agnostic. That is, which features represent real content, not artifacts. Given the feature map from the previous frame, SPM computes a weight matrix using a lightweight convolutional block and a sigmoid activation. This matrix acts as a filter. It suppresses regions dominated by degradation and preserves only the most informative, stable content. Then, the module combines this filtered version of the previous frame with a propagated feature from 2 frames ago, using element-wise multiplication and addition. The result is a clean, content-rich feature that's passed to the current frame. This selective process ensures that only high-quality, temporally consistent information flows through the network. As a result, temporal modeling becomes robust even when degradations change over time. To complement this, we introduce the Lightweight Enhancement Module, LEM, a compact block designed to handle each degradation type within a frame. LEM consists of 2 dense blocks and a degradation-guided attention block. The dense blocks capture fine-grained spatial details through multi-level feature fusion. But the key innovation lies in the attention block. It extracts degradation cues from the input feature and uses them to modulate the attention computation. Specifically, the query and key are multiplied by the degradation cues before the attention operation. This forces the model to focus on degradation-relevant regions, like noisy patches or blurred edges, and adaptively compensate for them. The result? A per-frame enhancement that's both efficient and adaptive, without requiring large networks. Together, SPM and LEM form the backbone of LaverNet. The architecture begins with a shallow convolutional block and 2 LEMs to extract initial features. These are fused with the selectively propagated features from the prior frame. Then 3 more LEMs refine the result. Finally, an upsampling block reconstructs the high-quality output. And because the propagated features are already clean and content-rich, the model can maintain high performance even with minimal parameters. Let's look at the results. On the DAVIS and SET8 benchmarks, standard datasets for all-in-one video restoration, LaverNet achieves 32.6 dB PSNR and 0.8967 SSIM on DAVIS test with time-varying degradations, outperforming much larger models. For instance, it exceeds PromptRestorer, a strong all-in-one image restoration method, by 1.2 dB in PSNR and 0.027 in SSIM, despite using only 1.5% of its parameters and 2.8% of its runtime. Compared to video restoration models like EDVR and RFDA, LaverNet not only achieves better results, but also runs over 10 times faster. But the real test is visual quality. Look at the tennis vest sequence. Existing methods produce blurry, artifact-ridden outputs. Even lightweight models like STDF and LaverNet struggle. But LaverNet restores the fine wire mesh structure with sharpness and clarity, nearly indistinguishable from the ground truth. In another example, helicopter, under noise and compression, LaverNet reconstructs clear outlines and smooth textures, while competitors fail to remove noise or recover structure. We also tested on different degradation combinations. noise and blur, noise and compression, blur and compression. In every case, LaverNet matched or surpassed larger models, often with significantly lower computational cost. Ablation studies confirm the importance of each component. Removing SBM drops PSNR by 0.28 dB and SSIM by 0.0071, proof that selective propagation is crucial. Replacing the attention block in LEM with a dense block causes a 0.37 dB drop in PSNR, showing that degradation-aware adaptation is essential. And scalability. We built smaller and larger variants. The tiny version, LaverNet T, with just 96.4K parameters, still outperforms EverNet by 0.69 dB, despite being much smaller. The large version, LaverNet L, reaches 32.92 dB PSNR, proving that our design scales gracefully. So what's the takeaway? We've shown that strong all-in-one video restoration doesn't require massive models. By deeply understanding the problem, particularly how degradations interfere with temporal modeling, we can design a lightweight network that thinks selectively. LaverNet doesn't just restore videos. It filters out the noise, propagates only what matters, and reconstructs content with precision, using a fraction of the resources. This work demonstrates that efficiency and performance aren't mutually exclusive. With clever design, we can achieve robust, real-world video restoration in a compact, deployable form. LaverNet is not just a model. It's a new paradigm, restoration through selective intelligence. And it's just the beginning.